Hey, welcome to Beyond the Forecast. That's Steve. That's me.
Jeff.
I wanted to push another button today.
Tried to match the snaps.
Yeah, the snap at the end of the intro.
Shout out to the marketing team for building that graphic.
Yeah. So we're talking about satellites first of all today. The TEMPO satellite. The TEMPO satellite is a tropospheric emissions monitoring pollution satellite.
Tropospheric emissions monitoring
pollution. Yes. So
TEMPO.
Goes east, goes west. You know
Yep.
those satellites. We
Taking
use
pictures
those
from space.
Yeah, we're looking at clouds. We're looking at hurricanes. This is a very similar satellite to where it's positioned.
Gotcha.
Geostationary.
But just a different mission, different role.
Yes. So its goal is to basically understand what's going on in the atmosphere column for different types of pollutants.
Oh, that's cool.
It's really cool. It's a really fascinating.
Really cool.
It launched in 2023 on board April 2023 on board a SpaceX Falcon 9 rocket. And it has been in operation since mid-2023 after they did some initial testing. And now we have data of it, but we're not going to talk all about it right now. This is the cool part of this. We're going to head over to NASA Langley.
Get up on the peninsula.
Yes, we're going to the peninsula now, and we're going to show you more about the satellite from some of the directors and the team on this satellite. So we'll be back here in the studio after our talk. I'm here at NASA Langley, and we're talking about TEMPO with the experts. Welcome.
Thank you.
So tell me, what is TEMPO? And tell me also, how long have you worked on TEMPO?
So I've been working on TEMPO for probably about 7 or 8 years now. TEMPO is the Tropospheric Emissions Monitoring of Pollution mission. So it's a combination mission between NASA Langley Research Center and the Smithsonian Astrophysical Observatory to study the pollution in greater North America and how it moves across the continent, where it comes from, where it goes, and hopefully to begin to influence weather models, pollution models, air quality models, and help the general public with knowing what your air quality is going to be outside that day, knowing if you've got asthma, for example, can I go outside, should I stay inside, things like that.
And tell the viewers who you are once again. How long you've worked on it for years? So who are you?
So I'm Kevin Doherty. I'm the project manager for TEMPO.
And so the one thing that I'm wondering about with TEMPO, it was launched in 2023 on board a rocket, a SpaceX rocket, but this is a satellite that is not like other Earth observing satellites that flies around the Earth very quickly. This is one that's more geostationary, correct?
Correct, yeah. So we take advantage of being a specific distance from the Earth, and that allows us to stay over the same spot on the Earth at all times. What that does is instead of coming around and flying over different parts of the United States once per day or twice per day, we're actually staying directly overhead, and we can observe. Allows us to do hourly time measurements across the entire continent and just go back and forth and back and forth. If we want, we can even zoom into a smaller area and do like 10-minute increments to look at it. So yeah, so for being in that special spot, there's a lot of other satellites out there. We've forming a giant ring around the Earth. For example, a lot of people are used to using DirecTV and other satellites like that, where you point your dish and you point at a specific spot in the sky, and you reach out to one of these geostationary satellites.
So what's an advantage of being geostationary versus being polar in terms of the distance that you are? Because when you're geostationary, you're really, really far away from the thing you're trying to get image and data from. So is that a disadvantage for how the instrument works?
So it is a lot more challenging being 22,000 kilometers up and trying to look at actually, I need to go back. 22,000 miles up.
22,000 miles. Yeah, I was wondering. I was thinking. Wait a minute.
35,000 kilometers.
Yes.
22,000 miles up, and looking down at the Earth from that far away. When you hear about things like the International Space Station, you're talking more in the 300 to 400 kilometer range. So much, much, much closer to Earth. So we are about 10 times as far away, trying to look down at the surface of the Earth. Now, being far away does have those disadvantages, but we built the instrument specifically to be able to zoom in on the Earth and see what we wanted to see. So we're looking at little spots on the Earth, roughly about 1.25 mile by about 3 miles side to side.
Wow. Okay.
So that's how big each one of our individual pixels is. So being up there allows us to actually look across and look at an hourly time scale, as opposed to just getting 2 quick looks per day or 1 quick look per day, depending on where you are.
So we're looking at the Earth, we're looking at North America and the United States specifically. What are we looking at? What are we measuring?
Yeah, so we're actually, as the light from the sun comes down to the earth, it gets reflected back by all sorts of different gases in the air. You'll often see that the sky is blue, for example. But our instrument actually looks at it in much greater detail, looks at a variety of different colors of the light, and we pick out the different colors. And what we're able to do from that is see exactly what different gases are in the air. For example, nitrogen dioxide, which is a common emission from cars, power plants, things like that.
And that's NO2.
NO2.
Okay.
So that's in the air everywhere. And what we're doing is we're looking down, and by seeing how much of specific colors of light is reflected as the sunlight comes into the earth and reflects back, we're observing that and able to tell you exactly how much nitrogen dioxide is in a particular area.
So nitrogen dioxide, like you mentioned, burning of fossil fuels from one thing, or from vehicles, power plants, that's where we're getting one of the sources of it?
That's correct.
What's another source of nitrogen dioxide?
So, yeah, I mean, any kind of burning, if you're talking wildfires, you're talking things like that. And what we've noticed is we can track different pollutants, whether it be nitrogen dioxide or some of the other ones. If there's a wildfire in California, you can track it across. There have been cases in the past of wildfires, even all the way on the West Coast, setting off air quality monitors in, say, Boston, for example. So just because it's nowhere near you doesn't mean that the air isn't flowing that direction and bringing it to you.
Can you get nitrogen dioxide from thunderstorm activity?
You can get, it's one of the things that you can get, but there's also a few other things that we're measuring that we're particularly interested in seeing how lightning affects the different. It actually creates pollutants.
Okay.
Some of them are very short-lived, but it's kind of neat to see as thunderstorms move through how the lightning's creating different things.
Is it because it's heating the air so rapidly because the temperature is so hot?
Yeah.
So it's burning.
It's essentially burning the air a little bit.
Wow, that's fascinating. Never even thought of that. So we are looking at this, but we're looking at the instrument needs light. So this is essentially like a visible satellite in a way. So we're getting daytime data from sunrise to sunset.
Correct, yeah. And
not anything at night.
So we're looking at both UV and visible. One of the interesting things that since we launched and since we started operating, we decided to take advantage of the fact that we are up there all the time, all day, all night, and we started looking at city lights and twilight and looking at, well, what does it look like shortly before the sun comes up or shortly after the sun goes down, and what can we learn from that? So the scientists are just now starting to really dig into some of that data. So not only during the daylight, which is our primary mission is to look at the light during the daylight, but we've also started extending that and seeing how the city lights behave and how some of the pollutants track during those times.
So can you see someone with a modified pickup truck and they shoot out the black smoke out of the exhaust pipe, or is it not that type of resolution?
Not quite that good. We are still talking about 1.25 miles by about 3 miles, but that's the neighborhood scale, which is much better than we've gotten from a lot of other instrumentation. One of the advantages of being able to do coast to coast, all the way from about Mexico City to the tar sands in Canada, is that we can see all the way across the country. If you pull up air quality data and you look at it, the urban areas have a lot of air quality monitors, but once you get out into the rural regions, there aren't nearly as many. And you think nitrogen dioxide is one that everybody thinks about.
Yes.
And it's one of the first things that comes to mind. But when you start talking about other pollutants, like formaldehyde is actually a rather large one, which isn't just used for preserving things. It's also generated from farmlands. And we can start to observe formaldehyde as well. So farms generate a type of pollution. Forests can absorb some, but also create it with fires and things like that. So it's not just human activity, but all sorts of activity across the country. So
I'll pull this up full screen, but this is the viewer that I found on your website, just looking at the Earth data. There's a lot of different things. This is the nitrogen dioxide. So we can zoom in. I looked at it earlier. We can zoom in, and you can see the changes throughout the day based on traffic patterns.
Correct.
So what can people do when, I'll link it to you, what can they do to view this data, and what can they learn from this?
So the Earth Data Now is or Earth Data Search is the best place to go to look at the tempo data if you want to dig in, if you want to look at different areas, you want to look at one of the variety of different products. You mentioned nitrogen dioxide, but there's a whole host of others as well. And you can go in, you can look at different time periods and kind of zoom in. And that one of the nice things is we're when some event happens, we also like to do some publications, and we work through our Office of Communications and release smaller videos. For example, when there were prescribed burns over in North Carolina, or other activities going on, we'll sometimes release special videos and products.
I saw on here too, when I'm looking on this, there's a bunch of different other parameters and data sets that we can see, like ozone. So what are we tracking when we're looking at that?
So ozone, a lot of people have heard about ozone in school. Ozone is great in the upper atmosphere. It protects us from a lot of UV rays, keeps us from getting sunburns quite as quickly. But when the ozone gets down here to the lower atmosphere where we live, it actually is very harmful to those with asthma. It's one of the things that people need to keep an eye on.
Okay.
Ozone is rather difficult to discern from space when you're looking at the reflected sunlight, but we have some of the world's foremost experts on what we call retrieval, on measuring that and interpreting the data for ozone. So that product was one of the big reaches that we were doing, and we've just started releasing some of the data for that, and we'll continue to do so throughout the life of Tempo.
So this was launched in 2023, obviously not in position that same day. It had to get in position, get into the proper orbit, and everything needed to be tested out. So how much data do we have so far from Tempo?
So up through October of 2023, we were still checking out the instrument. We had to let the spacecraft go through all of its checkouts and be ready to operate.
Okay.
After October, we started collecting data for real scientific uses. It took us a little bit longer to get some of the data products released, but what we did was we were going back to October of 2023 and releasing all the data products from then on. So you'll be able to go back that far.
A little bit of quality control, make sure everything looks good. And then it's like, all right, it looks good, it's accurate.
Yeah,
just want to make sure it's correct.
We've got a whole team of people dedicated to doing what we call validation, which is looking at ground-based measurements and looking at aircraft measurements and comparing that to our data and helping to make sure that the data products and that we're retrieving off of the instrument are accurate.
That team is located here at Langley?
So some of them are at the Smithsonian Astrophysical Observatory.
Okay.
There's some components at Goddard. There's Goddard Research Center, Space Flight Center up in Maryland, and some the team here is largely focused on the project management and overall execution.
Got it. There's other things that were on here too, and one of them I want you to teach me because I've never heard this before. It's called cloud pressure. What is that?
So cloud pressure is a fancy way of saying how bright are the clouds, how thick are the clouds when you're looking at them from
cloud
space.
Thickness.
And because the clouds will reflect the vast majority of the sunlight when it hits them. Some clouds we can see through a little bit, if they're the thin and wispy, the cirrus version.
Yes.
But other clouds we really cannot see through. And so one of the things we need to do when we're looking at the data is be able to identify how much of our view was obscured or blocked by the clouds and how much could we see down to the surface of the Earth.
Got it. So when we're looking for nitrogen dioxide, for example, we need to have a clear sky so we can see down to the surface.
Yeah, so we can see some of the nitrogen dioxide that's actually above the clouds as well when we're doing it, but clear days are what we need to actually be able to see all the way down.
Do you know where the concentration of nitrogen dioxide usually is in the atmosphere?
I do not.
Okay, so let's think about it this way. So we burn the product, it gets mixed in the atmosphere, and there's still studies that are being done on that to this day. Because I know there have been, and I've done one before from Wallops, we've done some P3 flights and lower atmospheric study to see how the pollution is kind of being mixed in the atmosphere. So that still continues. So we're looking at a concentration of a whole column when we look at the pixel. Column, column, column.
And one of the unique things we're trying to do with the ozone in particular is not just do the total column, but also separate out how much is closer to the ground, the 0 to 2 kilometers or 0 to about 3 miles.
Okay, got it. So when I looked at the data, one thing that I've noticed on a couple of different days, especially when I looked towards the end of the day and right before the sunset basically happened or the termination line happened, the data would be a little bit brighter, as in it seemed like the amount of nitrogen dioxide increased suddenly. Is that something to do with the fact of how the sun is setting, or is it just because of the time of day when people are driving home and there's that rush hour plume of nitrogen dioxide and higher pollutants?
So we try to actually calibrate out where the sun is and then the angle of the sun and how much there's there. So when we display the data, it would be primarily driven by the amount that is there, if it's increased traffic. One of the interesting traffic studies that we started to look at was following the bridge collapse on the East Coast, and we were looking, and a part of an interstate was shut down. We were looking at the shift in traffic patterns from before that happened to after that happened, and how it was affecting different neighborhoods afterward as people took different routes to get to work and home from work.
That's a great experiment because you have a control, which unfortunately is the bridge collapse, but you have a control where you have something that's changed and you can test around it.
Yeah.
What else have you learned from Tempo so far?
So the scientists are just beginning to really dig into everything, and I'm sure they're going to continue to learn things for years and years to come. But some of the interesting effects are seeing how it works. We call it diurnally. It's how it changes throughout the day. How much rush hour affects things versus the middle of the day. When we're used to getting these other satellites in what we call sun synchronous orbit, they will almost always go over the exact same time of the day. For example, like 1:30 in the afternoon, it's coming overhead every single time. So you don't really get to see rush hour. You don't get to see other things. So Tempo gives us that insight that we haven't been able to see a lot before that, which is how does rush hour affect it? How does a fire that changes intensity throughout the day affect it? How do aircraft flights and their patterns affect it throughout the day?
Have we seen any changes based on just simple fact of seasons when there's more vegetation or there's less vegetation because of leaves falling off of trees and plants growing?
So we're still digging into that, but I suspect we will start to find some of that information.
Okay, so there's a lot to dig into here.
There's a lot to dig into, and we have a core science team that's been working on this for a very long time.
Okay.
But one of the reasons we really want to make the data available to the public is there's people at universities, there's people everywhere in the country that are interested in either using this data to see how their region is behaving, and others that have ideas on ways to interpret the data that we couldn't possibly have thought of ahead of time.
Sure.
And they're going to bring forward all their ideas. So our science team goes to conferences on a regular basis and interacts with a whole lot of other scientists across the country. And one of the fantastic things about Tempo is that it's so widely applicable to the general public, to you and I on a daily basis, that we see a very large part of some of these key atmospheric conferences being dedicated to talking about air quality, and people using the Tempo data that we didn't even know ahead of time how they're going to use it, how they're going to pull it. But it's just fascinating to see everybody using it.
So a lot of cool data that we're going to learn from over the months, over the years ahead, which is going to be really cool. Any chances or upgrades or future renditions of Tempo 2.0 that has the resolution that tightens it down so it's even smaller? Any plans for that or thoughts on that?
So actually, Tempo has what I call two sister instruments in other orbits. So the South Koreans launched one that's actually currently looking at Southeast Asia and looking at how air pollutants move there. The European Space Agency is launching Sentinel-4, which will have another air quality instrument on it, very similar to Tempo, to look at how pollutants are moving across there. Because not only do we get the transport across the country, but we get it across the world.
Yes.
And then inside the United States, Tempo is serving as a pathfinder on how we can do this measurement. Can we do it? Showing what the data looks like. From here, now that NASA has largely proven out the capability, proven out the technology, NOAA is looking at a satellite, one of their next generation weather satellites, and including air quality sensor, very much like Tempo, on board, so that we can continue even long after Tempo is done. So that's Tempo 2.0.
That's excellent. That's exciting to hear.
Transitioning from the science and the data and the pathfinding that NASA is well known for, and turning a lot of that over to NOAA to use operationally.
And we can't get too far ahead of ourselves because we still have Tempo 1.0 that's right up there right now. And we're just getting data from that. So how long are we going to have Tempo hanging out observing the Earth?
So right now we are funded to go through the end of next fiscal year, which is September of 2026.
Okay.
But during 2026, there will be a review. They do a review of all of the Earth science missions that are operating and that have exceeded their baseline life. So we're already just now past where we had hoped to get to. And they'll take a look and they'll determine how much and which which missions they want to continue funding.
What's an advantage to having an Earth observing satellite like this versus just having a bunch of ground sensors that some might say, why don't we just set up ground sensors everywhere and we can do the same thing?
So that would be incredibly expensive to set up a whole network to get it. For example, Kansas does not really have a whole lot of air quality measurements in it right now, but yet, as I mentioned, the farms are a creator of one of the types of pollutants that we're looking for. So that the pollutants are everywhere, and they're constantly moving and changing, and some of them change throughout the day. But by having that satellite, you really get the coverage of the whole area, versus it would take thousands upon thousands of individual little sensors in order to try to do that on the ground.
Anything else that we should know about tempo that we haven't talked about already?
Not that I can think of.
Okay. All right. Well, good. See, I stumped him on a question finally. No, I didn't mean to do that. But thank you very much for your help today, Kevin. This is good information. I'll show everyone where we can find this data, where we can look at this. So we can look at the past day. We can look at the past few months. There's a lot of data here. So thank you very much.
Thank you.
All right. Thanks. Back to you.
All right, we're back.
Yes, that was a fun conversation. A lot of stuff. Now, cloud pressure. When I saw that there was a variable on the site, let me pull up the site here. Let's see. I'll hit this.
You got it. We got it.
Right there.
There it is.
So this is a site. So one of the variables, and I didn't load it up on here, it's called cloud pressure. We talked about it in the conversation. It's basically just where cloud cover is.
Yeah.
So when you look to the site, and this is in partnership with Harvard, you can look at the data of the NO2 pollution, of the NO2, the nitrous dioxide.
This is live. Or you're going back, this is 1:07 p.m.
This is to 24th at 1:07 p.m.
24th. Today is the 25th? What's today that we're recording this?
We're 25th.
25th. Okay.
Yes.
All right.
So this would have been Tuesday's data
Gotcha.
that we're looking at here. So we can zoom in, and here's the resolution that we're talking about, the pixels. And this is a lot better than what we've seen from previous observing satellites and remote sensing.
How many square miles is that, a grid like that?
The grid,
pixels.
Yeah, we
Because
talked about
that's
it. Let me
like,
see.
I mean, that's...
2 kilometers per pixel north and south, and 4.5 kilometers in the east and west direction.
That's great.
So this is
Look
in the
at that.
morning, and then now as we go into the midday hours, you can see how the pollution in
Picks
certain
up.
areas, the nitrogen dioxide picks up.
It makes sense. The noon hour here is where you have it stamped up, the pollutants from the morning commute, and then businesses getting up and running, let's say in the 4 to 6 hour window from 6 a.m. to noon or 8 a.m. to noon, all that stuff adds up. So you're visually seeing that. Wow.
Yes.
I'm going to go back there. That's at the 3 o'clock in the afternoon.
3
And look it
o'clock.
up towards Richmond as well.
Yep. And that's
That's
right around
awesome.
rush hour for us, for when the shipyards and other things get out.
So this you said was nitrogen they were measuring?
This is nitrogen dioxide. is
Nitrogen
what we're looking
dioxide.
at. So burning of fossil fuels,
Yep.
burning of things. We can look at some notable dates on the side here. The LA wildfires. It'll go over to LA.
Poke over to
Look
LA.
At that.
Look at that. This was January 8th, this was January 8th, 2025. The big fires that they had to start 2025. That
Yes.
feels like 8 years ago at this point. My
Yes.
goodness. And you're getting a real look at the thickness of that. Wow.
you can see
the
how
darker
that
colors
spreads
are
across-
rich on the scale.
Yeah.
The
Look how it spreads across a
concentration.
populated area too. So it's a really cool website, and you can really take a look at a lot of different things on here in terms of your community, the air that you breathe. You can see even just on the 24th.
For air quality too.
Air quality,
Yeah.
yes. It's great information. It's a really cool way. So there were some questions that during our conversation that I was asking them saying, hey, what about this? What about that? What do you think this means? And they don't quite know yet because they're getting the data. We have to spend more time doing the research. So that's why they're putting it out to the public so we all can take a look at it. And if you want to dive into it and you want to do a study on it, you can do it on your own.
The scientific method, you know what I mean? Make your observations about the data that you're getting and then build a hypothesis out of that and go for it. That's really, really cool. And it's also cool seeing that in real time. I mean, a lot of times we're so used to just that stuff being there and we kind of already have the answer or the solution to it. But this is new so that it's I mean, did they give you the date of when it was first collecting data? When I know they launched it in mid 2023. Was it like in place collecting data at a certain time? So it's like right now, how much of that data has come in? You know, that sort of thing. But it's just cool seeing how that is a delayed effect because a geostationary satellite's got to get in position. That's the first thing it's got to do. It's got to get in orbit. And when we say geostationary satellite, we're meaning it's at a fixed location and it's rotating with with the Earth.
It's always looking at the same
It's
spot.
always looking at the same spot.
Yes.
Yeah, so this is
This
you can
is
see all
last
the way in the
year.
middle of the Atlantic, you see that line where it just cuts off. That's the end of the picture that it's sending back. And then on the left
Right.
side, I'm assuming the same thing. Yep.
There's
that's-
a data
that's
cut right
the
there.
Fixed position it's taking, yeah.
Yep, that's the cut of
North
data.
America,
so
yeah.
middle parts of Mexico all the way to middle parts of Canada, essentially,
Yeah.
is where they're getting data.
Most of North America, yeah.
Most of North America. I'm just looking at the dates here. I don't know how far back it
Yeah,
does
sure.
go, but it does go back quite a ways. So
2024, you're in 2024 right
yeah,
now.
so I mean,
yeah.
they have data. I remember Kevin saying that as they
so
made
cool.
sure that the data was quality early on in the satellite being kind of running, they said, okay, that data's good. We can release that too. We can give you all that. Because there's no
Gotcha.
point to release data that's bogus data where an instrument needed some calibration.
Of course.
So
Yeah.
they're not hiding anything. It's just more so if it's bad data, why look at it?
Yeah, I mean, you got to tune the guitar first before you start playing it. So,
Exactly.
Yeah, so that totally makes sense. Jeff, it's so cool that this stuff's right in our backyard.
It is. So shout out to the team at NASA Langley. That was really fun to talk to them. The Tempo team, they're not just all here at Langley. They're at other locations like Goddard too. But shout out to them for letting us come by and talk about the
Super
Tempo
cool.
satellite.
Tempo satellite, love it. And we hopefully have some more, right? I mean, you're planning to get
yeah.
up on the Eastern Shore, look at some more satellites and stuff.
Yes. About the GO satellite.
The GO
yeah.
satellites,
Yes,
yeah.
the GOs.
And that's one of the funnest things. That's one of the funnest things I think we like to explain at the school talks when we go to the elementary schools, the classrooms, and teachers are like, hey, come talk to our kids about the weather unit, and we get to mention the satellites because. You know, kids understand what a picture is. They understand that, you know, whether they're phone or a camera, and you could take a snapshot of a moment in time, and that's what these satellites are doing. And then they're just sending back a different type of photo. You know, like that one's probably that's the one that's coming back, and it's the what do you call it? The print one. What's that one? Comes out
The Polaroid?
yeah, this one's
Yeah.
like the Polaroid
Yeah.
photo. It looks a little bit different, and then you have like the super high res photo that comes back, and it's this satellite kind of deal. So that's one of my most enjoyable things to explain to the kiddos is that these things are just floating up there in space, taking pictures of real time of what's going on in the atmosphere, and then a lot of times sending it back to us so quickly in a matter of minute increments. Every minute, you get a photo from space, which is just wild to think about.
I'm looking to see if there's something that's like a Polaroid. This manual works. So when you took a Polaroid, did you shake it to make it develop faster?
Yeah.
Did that even work?
No, I don't know, but that's the lyric in the Outcast song. Hey,
Yeah.
shake it,
Hey,
shake it like a Polaroid
Picture.
picture.
Yeah.
All right. Awesome. We're not
okay.
doing that with this data though, because that's too good of data to
Nah,
shake
we're not
around
going to
like that.
So we're going to take a quick little break here, and then we're going to come back. We're talking about humidity, dew points, sweating,
And we've
why
been-
it works, how it
We've
works.
been stuck in it. We've been stuck in it. It's been
it
tough.
doesn't end.
It's been tough.
It is in. So we'll be right back. All right, welcome back. We're talking about humidity, transpiration.
You sweating yet?
Yeah, it's hot in here.
It's
There's fans in
ridiculous,
here.
man.
Is there a wide shot?
I know
No.
there. Oh, hang on a second. I put it down. I put it.
Oh. Uh-oh.
Uh-oh. There's
See? We're trying to stay cool in here. This forecast is brought to you by Lasco.
This is, I think, what all of us are like trying to do now in this heat. It's just ridiculous. Standing by the box fan. You ever do that as a kid? Be
Yeah.
like Darth Vader.
yes.
You know, you ever do that voice?
Oh, yeah.
Sorry.
Yeah. Oh, we're having too much fun.
Like, couldn't have too much fun here. That's the best part about. That's the best part about this Wavy Plus platform, man.
Yep, we can have some fun. So, oofta, humidity.
Oofta, big
Yeah,
time. And
that's-
transpiration, too. It's a big word.
Yes, we're going to get into transpiration in just a bit, but dew points, the temperature at
yeah.
which dew forms.
Yep. Temperature at which dew forms. A lot of times I kind of describe it as this is the value the temperature needs to get to be 100% saturated. You know, what's 100% saturation? 100% saturation is when dew forms.
Yes.
Is when the water in the air solidifies, basically.
Yes.
Becomes a liquid. You
Yep.
know, so a dew point, that temperature is a scale to gauge what level in the atmosphere the water's at, the water vapor's at, basically, you know, and how that relates to the temperature here. So we always just say the higher the dew point value, the higher the humidity, because there's just more water vapor in the air, but it's in a gas format,
Right.
Because we're not at the dew yet. We're not at
Saturation. We're not
Yeah.
saturation. Dew points, 80 degrees. muggy, I guess, is, I don't know. Muggy seems not enough for 80
Yeah,
dew
because
points.
and this is the one thing I love about humidity. It's all relative. You know what I mean? Like you could have a day that feels muggier with a 70-degree dew point because the temperature, is closer to 70
Yes.
degrees. And you could have a day where it may not feel as muggy, but the dew point's higher. So yeah, it just kind of represents the amount of water in the air. But the relative humidity is where it gets tricky.
Different.
This is where it gets a little bit tricky here. So a good friend of mine always said the dew point is the decider.
Yes.
The dew point is a really good indication how the air is going to feel to us. It's going to decide how the air feels to you amongst the sunshine, amongst the actual temperature and all that kind of stuff. But when you're talking about humidity, how much is the humidity going to affect my hair? How much is it going to affect how long it takes my sweat to dry or how quickly I do sweat?
Right.
All depends on the dew point. Now, the relative humidity is where it gets a little, it works.
It changes.
Not all the time, basically.
Right.
So if you're looking at your app and you say, oh, how humid is it today?
Yep.
And you look at the relative humidity and you look at the percentage, there will be days where the percentage of relative humidity is high, but it doesn't feel humid. And there will be days where the relative humidity is low, but it feels humid.
Yep.
Because the dew point and the temperature range, that just depends on where the dew point is.
Correct. The relative humidity is a great tool for, and I'll just pull up the last thing here, a great tool for inside of a building.
Yes.
To measure how humid the room is for mold growth, or if the air is too dry. You don't want the air inside of a home too dry. You want it to be close to around 50% generally, 40 to 60. 60 is starting to get a little high.
Yeah.
But generally around 50%. That's a comfortable thing for us as humans. It's a good level for removing the chance or really reducing the chance for mold growth.
Yes.
Because that can be a big problem if you have a crawl space that's too humid, if you have a bathroom that stays too humid and mold grows on the walls or on the ceiling because of the humidity. So relative humidity, excellent for inside use or excellent for any exterior work that it's sensitive to, like painting or other type of applications where you want to make sure that what you're trying to do is appropriate with the humidity.
Yeah.
But you have to remember, outside, it changes all the time because it's relevant to the temperature.
Yep, and relative to temperature.
Yes.
That's the big thing here. The
the
relative
takeaway.
humidity is relative to the temperature, which means the dew point value will be different relative to the humidity, and then we go back to that other scale. That other scale defines the how it feels to us: the muggy, the humid, the moderate, the refreshing, the pleasant.
Right.
That's a different value. So in this instant here, when we're talking about percentages, let's just say the temperature is 100 and the dew point is 10.
Okay.
I mean, the math is not right here,
Right.
but that's, you could just picture, okay, that's 10% relative humidity, because 10% of the air is full of water.
Correct.
Right? That's
correct.
how we describe it.
Yeah,
right?
correct.
In the middle, when you're at 50% relative humidity, 50% of the air around you is full of water.
Yes.
And then you go up from there. If you pick a piece of the air out and you say, all right, 75% relative humidity, 75% of this piece of air has H2O in it, water in it.
Right.
That changes, though, based on where the temperature's at. So if you have an 80-degree temperature day and then your dew point is 40, that's a really low percentage, and you're, okay, it's not going to feel that humid.
Correct.
But if that dew point is up to 70, 80-degree temperature and 70-degree dew point, they're really close to each other.
That's humid.
That's like, in this instance, saying like, oh, the water's like, the air is 90% full of water. Like, that's going to feel humid. Mm-hmm. But then it doesn't work all the time like that. If it's your favorite type of weather, Jeff, it's snowing.
Yes.
It's cold.
The humidity is still high when snow's coming down.
Humidity is still high when snow's coming down.
The relative humidity, rather.
The relative humidity.
So the dew point could be 28.
And the air temperature could be 29.
Yep.
And you're talking about a 29-degree temperature and a 28-degree dew point. Those are like, they're right on each other.
Yep.
So that relative humidity is 99%.
Yep.
And if you looked at your app and say, 99% relative humidity, it's snowing outside. I'm not
Yep.
sweating relative to the temperature.
Correct.
80, just use today's example, 95 degrees out, and the dew point's 90 degrees, we're melting.
Right.
It's ridiculous.
Right.
It's absolutely ridiculous. So relative humidity works only when it's hot out, I think.
Yeah,
For us to determine how the air feels to us humans.
Comfort.
You know, when we're talking about in a controlled space, like you said, indoors, relative humidity is the best to use for that.
Because generally the temperature in your home is going to be about the same. You set your
It's
thermostat
constant.
to something.
Yeah.
No one's setting their thermostat to 95 degrees and no one's setting their thermostat to 45
Correct.
degrees.
Yeah.
So it's
If you're sane, it's probably around 72.
something like that.
You know,
Yeah.
either side of the spectrum, maybe 65 or 78.
Yeah, the old age-old debate is 68 or 75. I don't know, but that's a good point, and that's one thing to remember for how much water is in the air. Just using the relative humidity, that's a good way. to think
And
of
also
it.
that plays a role into how much we sweat and water going into the air from things around us.
Yep.
You know, I'm trying
we
to
don't-
cue
we
up
want to talk about that
transfer-
first. Why do we sweat, or do we want to do
What-
transpiration first?
Let's do why we sweat, I think, because we're on
Okay.
humidity right
All right,
now,
let's go back to
It's
that.
I think it's just a little bit easier in a sense which we are mentioning the humidity in the air and describing it as water content in the air. All right, so the best way to describe this, why we sweat, and why we sweat a lot when it's hot and humid out,
Yeah.
when the air has a lot of water in it
Okay.
and the humidity is high, I'm going to say that, the dew points are high.
Yes.
When the dew point value is high, that means the air has a lot more water in it.
Yep.
So think of it like you're getting out of the shower or the pool and you grab a wet towel to dry yourself off with. It's gonna be tremendously difficult to dry your sweat off with a wet towel. Mm-hmm. The sweat on your body needs to evaporate for your body to cool down. That's why we perspire.
Well, first of all, if I grab a wet towel coming out of the pool or the shower, I'm going to say, this is disgusting. Why is it still wet? And where's my towel?
Where's my dry towel to dry off with? Where's my dry towel to towel? So when our body temperature rises, we have that little thin layer of heat that is basically radiating out of us to expel that heat to try to cool things off.
Correct.
That heat condenses when it meets the water in the air. When it meets the air around it, it condenses into sweat. So now we have all this water on top of us, sweat, this salty, this icky stuff. When the air is dry, that sweat, just like grabbing a dry towel, dries off really quickly.
Yes, it does.
And it goes through evaporative cooling.
Evaporative cooling.
So when water or sweat, liquid evaporates,
The air cools.
the air immediately around it cools off.
Yep.
So that's like, you get out of a pool or a sweater or whatever, or a shower, and like a gust of wind comes, you go, whoo, it's
Yeah.
cold. That gust of wind is basically drying the water or the sweat on your skin, forcing it to evaporate, forcing the air immediately around it to cool off so it feels colder.
Even
So-
when you get out of the ocean on a super hot day in the summertime, you still feel cooler as
Yep.
you're drying off. You don't feel like, oh, I'm not instantly hot yet.
Yes, because
Staying
the
cool.
water is drying. So that's what we need to cool off.
Yeah.
We need our sweat to evaporate. We need the sweat to dry as it's released from our skin. However, that is tremendously difficult to do when the air is already so full of water. That's what we pull in the wet towel analogy. So if we need our sweat to evaporate, dry to eventually cool our bodies off, that process is going to happen quicker when it's really dry out and you grab a dry towel.
Right.
That process is going to be tremendously slow if you grab the wet towel or the air is already so full of
It's already
water.
saturated.
Exactly. The air is already so saturated. The dew points are elevated. The sweat just takes so long to dry, so then you just end up sweating more.
You can calculate the temperature that the air will be after the water evaporates.
I don't know that equation off the top of my head. I can't
Wet bulb
remember.
temperature.
Oh, there we go.
Yeah, wet bulb temperature. So,
It's the last you're going to see of me on here anyway, so we're good.
yeah, that's another topic. But yeah, in my Meteorology 101 class, the late, great Dr. Arrett and Dr. Hornbuckle, my professors at the time, we had a sling psychrometer, I think is what it's called. So you take basically it's like a stick, and then there's a hinge, a pivot point, and then there's a thermometer on the end. The thermometer that's on the end is wet. It's soaked with a wet rag.
Yeah.
So you spin that around, you cool it down,
and then when it
evaporate.
completely dries,
You get the wet bulb
You get the
temperature.
wet bulb temperature. What
Yeah.
temperature when it's done basically drying? What's the new temperature at?
Right.
Right. That's also how snow is made. On
That's
snowmaking.
right. That's right.
Snowmaking, right? They kind of force that to happen.
Yes,
You
they
know,
do.
They force that to happen.
Yeah, we did
So,
that story, a couple of years ago
a couple
now?
years ago. Go find it on YouTube.
Yeah,
we
we'll
should
have to
loop that on Wavy Plus.
Yeah.
Oh,
all
that's
day.
a new episode for the winter. You guys can re-loop that and talk about the whole process.
Yeah.
PIVNERT, PV equals NRT.
Hey, if it gives me a reason to go skiing, I'll take it.
Yeah,
So,
right.
I hope
That's what you could tell that's where our minds are going because
Yeah.
we're getting sick and tired of all this big time sweat here.
on the day that we're recording this, since it's the 25th, 6 months from now is Christmas Day. So
Oh, how about
we're
it?
getting there. Yeah, we're
Yeah,
getting
we're
closer and
getting
closer
there.
to that.
We're getting there.
One more topic here. How much time do we have?
got a couple minutes.
Okay,
Yeah,
a couple
we got a
minutes.
couple minutes.
Let's squeeze this in. So first of all, a little caveat: the video on the left of the steaming plants is a generative AI video.
That's
That's
not
not
spinach.
accurate.
That's not spinach cooking down on the stovetop.
No, it isn't. So
looks
just
like
so
it.
everyone knows, I made that for illustration
Yes.
for this. So we're talking about transpiration and evapotranspiration. So you suck water up through the plant, it grabs it from the ground, from the previous rain, or from the groundwater, whatever the source is from. That water goes up the plant uses it, and it sweats a little bit. It lets a little bit of that water evaporate off of the leaves, and that's the transpiration part of it. So, excuse me, an environment with a lot of corn crop or a lot of big leafy plants,
gonna feel
not
more
just
humid.
prairie grass, but bigger plants, they transpire more than just a field of grass. So you can get a much more humid environment in a cornfield than you could in a prairie.
Which brings us to the Iowa cornfields.
Yes.
And your time at Iowa State.
Yes.
You know?
Dew points would get to 83 degrees.
Which is you're not even near bodies of water.
Nope.
Not even near the ocean, the bay,
Nope.
none of that. And it's just putting so much more water in the air, and that's what drives up the dew point.
It just drives it up. And the transpiration, you can't see it because it's not like steam.
This is gas, yeah.
It's just a gas.
H2O
But
in gas form, water vapor.
could you imagine if it was that much transpiration? You could see the, oh no.
Well, now I'm gonna think of that every time, when you're sweating on a cold day and you're like steaming and you
Right.
see the heat coming off of you. I'm gonna be like, transpiration.
Yeah.
Not quite, but yeah,
Not quite.
but it's kind of that visualization in a way here. So just adding more water into the air, not only from your typical evaporation from water surfaces on the ground, you get that from, Jeff was mentioning, from plants, whether it be grass, trees, leafy things, crops, whatever. So it's kind of cool how that could absolutely change, make a more humid bubble
Yeah.
around that kind of stuff.
Do we have time to squeeze in a question from a viewer?
Oh, yeah, why not?
Yeah, we have time.
Yeah,
Yeah.
we got like 2 minutes.
2 minutes. Okay, so this is a quick question I just got today, actually.
Oh, great.
This is from Barry Minsberg in Norfolk. He says, it seems whenever we get very hot weather in the summer, the wind is blowing in from the west or southwest. With this latest hot spell that we've been having, he's seen the wind, and we have had the wind from the east, northeast, or even northwest. So why is it still hot, and why is it still humid with an easterly wind? So the humidity isn't changing much because we're not tapping into a source of dry air. That's kind of the easy answer for that part of it.
Yeah, like it's not like a post front, or there's not like a
Right.
cool front nearby to pull in drier air. I think it's just the way the high is situated in our current environment right
Yes.
now. And it might just be, it's also, I would say, those hot, humid days, as Barry mentioned, come from a day with a strong southwesterly flow or southerly flow, meaning the heat is coming from somewhere.
Correct.
Right now, the heat is just on top of us.
Yeah.
So there really isn't a breeze bringing in the hot air. The wind that I think we're kind of getting out of the east or northeast is just developing from more smaller scale temperature gradients.
Right.
Like temperature differences between the water at the north end and Princess Anne or Norfolk or whatever. Like it'll just change up the wind like a sea breeze in a way.
Mm-hmm.
So maybe that's kind of the way of dealing with it. When we have calmer winds on a synoptic level, that I think enables
The
more wind shifts,
microclimate
wind shifts to happen from different
does.
directions and stuff.
It does. And the water temperature, last I checked, was around 81 or 82 degrees.
So even a breeze off that is not going to do much.
doesn't do much. It may drop the temperature by a degree or two, but it doesn't do much.
And it did that at Norfolk International Airport. That's where we kind of record the temperature, and we hit 94 yesterday, but downtown Norfolk was still 100. So
Yeah.
it dropped the temps a couple degrees, but I mean when it's this humid out, it feels like 105 plus anyway. So
It's just
what
so
does it
hot.
matter?
Yeah,
You
it
know?
doesn't really
Yeah,
matter.
Yeah.
Oh, that was a good question. There's actually a second part of the question, but we don't have time for that now. We'll maybe get back to
Revisit
that
it, yep.
another time and probably do it on air too as well. So thanks again for tuning in, everyone. Thanks for joining me today, Steve.
Love it. This
It
was
was
great.
fun.
It was a great time.
Transpiration.
Transpiration.
Woo! All right. Well, hopefully we don't see as much transpiration in the weeks ahead. We cool it down. We get some snow.
Yeah, let's get a front here or something.
Yeah, something. All right. Enjoy the rest of your night.